I want us to look at what is called the intermediate value theorem. So enter, if I can spell it. So the intermediate value theorem. For this theorem, we're looking at some interval a, b, and it has to, our function needs to be continuous in that interval a, b in order for this theorem to work. So we're going to let our function f be a continuous function on some interval. Could be continuous everywhere, but we're going to narrow it down to AB. So remember, sometimes we could write intervals with brackets if you're including, or parentheses if you weren't including. And so basically here we have a graph. Find some value A here, some value B on our graph. And if for some reason this is continuous, and looking at my graph, I can tell that this is continuous on this piece. Notice that this point here, when x is a, this is my f of a. And notice this value here, b. This is my f of b. What this theorem says is if we have a function that's continuous on this interval a, b, and then there must exist any y value that falls between f of a and f of b. So there must exist some c value in here that would give us a y sub 0 value in here. So let me go back and kind of finish off what we were saying. So let f be a continuous function on some interval a, b. And if y sub 0 is any value between f of a and f of b, then y sub 0 is equal to some value c, f of c, where c is in the interval AB. Okay, so again, if it's a continuous function, we're going to look at our smallest y value. We're going to look at our largest y value for that continuous function. And any y value that falls in between this interval, because it's continuous, there must exist some value that falls between A and B that would give us that y value. So really where this could be helpful is for finding intercepts. I also want to say one other thing though, because it's possible that there might be multiple C values that give us that same Y value. Because what if our graph had looked something like this? And maybe this was our A here, and this was our B value over here. And so let's say, okay, this is here. So this is f of a. I can look at my graph. I can see there's no jumps. It's continuous. And this would be my f of b. And so let's say I want to see, because of these values of my y, I want to know what x value would give me back this y value. Let's see up here. This should have been more up in here. So notice that there's a couple different values in here that would give me this y sub value, y sub 0. There's another y value over here. That's the same y sub 0 point. And so there's another c value. So this theorem is saying that there has to be at least one value of x that will give us that y value if it's continuous. So again, this is really helpful if we find your value f of a and f of b are opposite signs. Of one another, then we know there's at least one x-intercept between A and B. Another way to say x-intercept, remember, were roots of f of x, or zeros of f of x on the interval AB. Okay, so pictorially, if you thought about it, makes sense. If you look at your graph, and let's say A was here, and you had your y value was negative, and you had B was here, and your y value is positive, it has to be a continuous function between these A and B. So in order to be able to connect these 2 points, there's something going on in here that we have to cross this x-axis at least once. So this theorem is helpful if maybe we want to find our roots of a polynomial. And maybe those theorems that we learned back in college algebra, rational zero theorem, Descartes' rule signs, all those things, we couldn't find any integer or rational zero that fell in between. And then we could start using this theorem by narrowing down this interval and continuing to narrow as we have negative and positive in between. And we could get a good estimate of what that's going to be.